Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings, I'm LeRoy, and welcome to the Natural Physics Experience, live in Costa Rica. As we continue on to find that force constant K, the amount of tightness or looseness that the quadrupole's magnetic field has upon the protons as they circulate through the quadrupole magnet around the synchrotron. Let us bring up where we left off. All right, here's where we left off, okay? Now, quick review. We had to insert what's called a drift space between our two thin lens approximations, right, to the quadrupole magnet, our two 2x2 matrices. We had to insert two drift spaces, all right? And here's where we are right here, all right? Once again, x0 and x0 prime, that in the radial or horizontally focusing direction, that's the phase space position of the proton with respect to the z-axis, that central trajectory, okay? And then as that proton goes through the first thin lens approximation to the quadrupole magnet, 2x2 matrix. And then from there, it goes into the first drift space, 2x2 matrix. And then there it goes into the second thin lens approximation to the quadrupole magnet, okay? And now remember, this first 2x2 thin lens approximation, that is the radially focusing, horizontally focusing, and axially defocusing, vertically defocusing element of a quadrupole magnet with a thin lens approximation. And this matrix, that is the axially or vertically focusing and radially or horizontally defocusing element of the quadrupole magnet. Both physical phenomena being represented by matrices. Okay, and so then after this third matrix, we have to also insert another drift space. All right, 4 matrices, right? First one, thin lens approximation of the radially, horizontally focusing element of a quadrupole magnet. Drift space. This one. axially focusing, vertically focusing, radially or horizontally defocusing element of a quadrupole magnet, thin lens approximation, drift space. And then when the proton goes through this quadrupole magnet, mathematically represented here by thin lens approximation, it comes out with new coordinates, a new x coordinate. Its horizontal or radial displacement with respect to that central z-axis trajectory, and how quick, how much that radially or horizontal position is changing with respect to how much the proton is going down that central z trajectory, okay? Original position in phase space of the proton goes through the quadrupole system, here represented by thin lens approximation with drift spaces included. Comes out on the other end with new coordinates in phase space, right? Okay, optics, right? Same thing. Okay, so we have 4 2x2 matrices. So what we need to do is multiply these 4 together to get 1. And what we do is we use this. Okay. When you have to multiply matrices together, in this case, 2x2 matrices, this is the formula that's used. And it is from linear algebra, okay? All right? You have the first matrix, A, B, C, D, right? Which is like our 2x2 matrix. And then you have another matrix, M, N, P, Q. So this is similar, right, to our 2x2 matrices. Okay, so when you multiply those two together, the way you do it is A times M, AM, plus B times P. Okay? And that gives you the first element in your matrix that you're going to result from. So basically, what you're doing is you're using this element and this element from these 2x2 matrices and this element times this element to get the first one. And this is what you do to get the other elements of your 2x2 matrix product. I'm not about to verbally go through this. If you're still with me, I'm so happy and I'm amazed and so grateful because a lot of mathematics I have been throwing at you, but again, I want you to see the importance of mathematics and astrophysics, and in this case, high energy physics, okay? So this is what you got to do, okay? So let us go back to our quadrupole magnet matrix. Okay, let's do that. All right. Okay. So after, here's our 4 matrices, right? That we have to multiply together to get one matrix. And from what I just showed you, that was an example of, for example, how you would take this matrix, the 2x2 radially focusing, horizontally focusing component of the quadrupole magnet and multiply it by a drift space, okay? Multiplying two 2x2 matrices together. And you saw how you would do that, how you would take this one and multiply it by the appropriate element in this one and so forth, right? You saw that, okay? And then you would do the same thing with these two. The vertically or actually focusing horizontally or radially defocusing element of the quadrupole magnet in the thin lens approximation and multiply that by a drift space, okay? So you would do that. And then, and as I said, I am not about to go through this with you step by step, no way, no how. But once you did that, where you multiplied this matrix by this matrix to get a 2x2, and you multiply this matrix by this matrix to get a 2x2, as per you saw that how you would do it, what I showed you. And then the 2x2 matrix that you would have from these two, you'd multiply that by the 2x2 matrix that you got by these two, okay? And when you do all that, this is what you come out with. This 2x2 matrix, okay, right here, which represents starting off with the proton's radial or horizontal displacement with respect to that central z-axis through the quadrupole magnet, and how fast that horizontal or radial displacement is changing with respect to the proton's distance along the z-axis. And as that proton goes through the quadrupole magnet, which is here represented by a 2x2 matrix that involves the multiplication of 4 matrices, one being the thin lens approximation 2x2 matrix of the radial or horizontally focusing element of the quadrupole magnet with a drift space, and then with the vertically or axially focusing element of the quadrupole magnet and another drift space. So multiplying those 4 matrices together, we get this mathematical representation of a proton going through a quadrupole. Thin lens approximation applied, everybody. Thin lens approximation. We're trying to get a starting point of that force constant. How tightly bound or how loosely bound the magnetic field of the quadrupole magnet in the synchrotron is on those protons. All right. Now, what we're going to do, you remember how we had to switch gears, so to say, from the dependence of the equations of motion of the protons, as opposed to expressing the dependence of the proton's horizontal or vertical displacement with respect to time. We wanted to switch that to the dependence of the horizontal or vertical displacement in phase space of the protons on respect to its distance along the z-axis. Remember? That's what we did, right? So what we're going to do right now, we're going to do the same thing. This 2x2 matrix that represents the quadrupole, thin lens approximation, force constant K, L being the length of the quadrupole, okay? Which if you remember, it was expressed as 19, the length was expressed as 19.758 meters, okay? All right. Okay, so now what we want to do now to get to that K is we want to go from a different reference system, okay? Instead of going from K to, we want to go basically, instead of the force constant K and the length of the quadrupole magnet, we want to switch coordinates and go from what's called the phase angle phi to the amplitude beta, okay? You remember this diagram I drew that shows the phase space ellipse for protons going through a quadrupole in a synchrotron, right? So what we want to go to, we want to switch from the force constant K and the length of the quadrupole to phi and beta. And on this phase space ellipse, phi is the angular displacement. If this is the displacement, if this is where the proton is, that's its angular displacement, phi. And this is the amplitude, square root of beta, from that central z trajectory out to where it is along the axis. And if you remember, let me show you this. Remember this diagram, similar to the phase space ellipse, okay? Same thing, right? You have a spring, physical spring with an object attached to it. Imagine in the synchrotron, the proton is being acted upon by the magnetic field of the quadrupole, okay? You can see a physical spring attached to this block. You can't see the magnetic force of the quadrupole magnet attached to the proton, but it's there. Just like this spring is attached to this block, that magnetic force is attached to that proton. And just like this spring has a certain tightness or looseness, which is expressed by K, the force constant, the magnetic field of the quadrupole magnet, it also has that force constant K that expresses how tight or how loose it is on the proton, okay? And because it's periodic motion, it repeats itself in phase space, you can express this in the same way, a periodic motion, which is expressed in that phase space ellipse I drew. Okay, all right, let's go back to this. Okay, so again, here's that phase space ellipse, which is equivalent to what I just showed you with respect to a physical spring with an object attached to it. All right. Okay, so now, again, we're going to switch coordinates from the force constant K and the length of the quadrupole magnet, but with the thin lens approximation, we're going to switch coordinates to this phi angle and this amplitude beta. And we're going to get a new set of equations of motion, okay? But I think that's pretty much enough for now, right? And again, this is on our way to getting a numerical value for that force constant K of the quadrupole magnet that's necessary to focus, to magnetically focus the protons as they circulate around the synchrotron. Okie dokie. Tune in next week. Same fat time, same fat channel.